Okay, I think I'm recording now.
Okay. So we're going to be looking at section 7.3, which is adding and subtracting radical expressions. We're also going to be multiplying and dividing still, like we've been doing, but they'll be binomial radical expressions. So like, for instance, 2 plus the square root of 3 times 3 plus the square root of 5. So we will be kind of using some of our forming techniques, and then rationalizing denominators that these binomials are a little bit different from what we do yesterday. Alright, so the first vocabulary word are like radicals. And these are radicals that have the same index and the same radicand. But radicand is just a fancy word for under the radical. Under the radical. So they have the same number underneath the radical. When you're adding and subtracting square roots or cube roots, it's just like adding and subtracting like terms. So like 2x plus 3x, we add the coefficients and we get 5x. The same thing's going to happen too because x's will be matching radicals or base radicals. So for example, 2 square root of 3 plus 3 square root of 3 is 5 square root of 3. You do not add the numbers under the radicals. That's what we're talking about radicals. You're going to treat them just like you would like terms. Down here it asks us to add or subtract if possible. There's a case that we are not able to do so. You want to check and make sure that the index is the same. You have square root and square root. You have 7 and 7, so that matches the definition of like radicals. So you can go ahead and add 7 and 3 to get 5 squared x. The next one, square root of xy, square root of xy, we can go ahead and add the right term to get 10 square root of xy. Now number 3, we have matching radicands, but each index is different. We have fourth root and we have a third root. Right? So these are different, therefore this is not possible. You literally cannot add or subtract because they're not like radicals. How about number 4? Okay. Can we subtract this? No. We have the same index of 3, but we have different radicands. We have different numbers under the radical. So this is also not possible. You literally cannot do anything to simplify that. Number 5, we should, which is square root of AB, square root of AB. So that would be 9 square root of AB. And the last one in this section is critical because a lot of students think that this is a 0, but just like if you saw just the point of x, it's technically a 1x. This should be a 1 square root of 7. So we can subtract these two minus 1 is 1 square root of 7, or just the square root. Now down here we have some geometry examples. Those of you that are in geometry right now, you just learned special right triangles, which can be a shortcut what we're going to be doing. So those of you that took geometry last year might remember that 45, 45, 9 using a very triangle. We have this special formula. We're going to do these using Pythagorean theorem. This is for everyone, because some people taking geometry, some people haven't. And some of you forget your special right triangle, so you can always use Pythagorean theorem if necessary. But this could be done using factors. So this in glass window shown, find the perimeter. Remember, perimeter is the distance around an object. This would be the distance around the whole rectangle. If each small square is 6 inches on each side. So like this is one of the squares. So this is 6, 6, 6 inches. This one would be 6, 6, 6. Now mistakes you think are like, oh, this diagonal would also be 6. No, it would not. Okay, because this is not a side of the square, this is actually the diagonal of the square. So we want to end up figuring out how big this part is. Call this P. And I'll redraw it over here. Okay, since we start with a square, it obviously has to have a right angle. And we have two legs of this now right triangle, 8, 6, and 6. So we'll use the Pythagorean theorem to find out what P is. If you were using special right triangles, this would be a 45, 45, 90 because the two legs are congruent. So those of you in geometry or those of you that suffer from us care about the S, N, S squared equals 2. So we should get what S, N, we should get 6 squared equals 2. But let's prove it with Pythagorean theorem. Plug in 6 for A and B, square them, add them, and then square root. Now we could break down the square root of 72, which we don't want to put 9 in because that's not the largest integer square that goes in, so we'll break this down into the square root of 36 and the square root of 36. Which will get me 6 square root of 2. Okay, so this little triangle, diagonal, 6 square root of 2. All of them are, they're all congruent. Okay, now some students will be like, oh, I'll just count them in half, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and multiply 7 by 6 squared root of 2, which will get me 60 squared root of 2. That would be inches. If you don't think that way, then you would just want to add all of the sides together. So you could actually figure out like how long this side is, which would be 12 squared root of 2. And when I said this side would be 18 squared root of 2. We know opposite sides are congruent, so this side over here would also be 12 squared root of 2 and 18 squared root of 2. So if you were to add those together, you're still going to get 60 squared root of 2. Okay, so those are just two alternate methods to find this number. Once we found the diagonal. The next one, also a geometry example, says a rectangular window shown is made up of 3 equilateral triangles. Who remembers what an equilateral triangle is? But all the sides are equal or congruent, or all the same length. Also, your angles can all be the same. Remember, there are 180 degrees that lie inside of a triangle, so if you divide by 3, each angle would be 60 degrees. Okay, which whenever we do this split up, we will end up finding some 30, 60, 90 square triangles. But again, I'm going to use Pythagorean theorem instead. So we have 3 equilateral triangles, 2 right triangles. The equilateral triangles have side lengths of 4 feet. So we're going to go and label all of the sides of the equilateral triangle with a 3. There are 3 equilateral triangles and 2 right triangles. They want us again to find the perimeter, so the distance around the other. So we're kind of doing really good. I know this side is 8. And since it's a rectangle, that means the other side has to be 8. What I'm missing are these 2 sides. Can I figure out what these little pieces right here are? Perfect. We're going to take 8, subtract 4 from that to get 4, and then divide it evenly in half. So this triangle over here, again, if we're using the square rectangle, this will be a 36 and 90. Okay, this will be your S squared root of 3, and your 2S. This answer should come out to be 2 squared root of 2. I'm going to start with Pythagorean theorem again. Just to make sure. Those of us that have efficiency numbers are looking at. But we all can do the problem. So this time, you want to make sure that you label the missing side A or B because it's a leg. We'll have A squared plus B squared whole squared by the number. subtract 4. Square root. And then we do have to reduce our radical. And we will get 2 squared root. Which again, we could have also gotten a lot faster if we didn't just have it. So now to find the perimeter, we just add all of the sides. So we have 2 sides that are 8 units long, and 2 sides that are 2 squared root 3 units long. Make sure you're only combining the numbers that you can. You can combine these integers or natural numbers to get 16. You can combine your like radicals to get 4 square root 3. You cannot add these numbers. Also, make sure you don't think that the square root of 4 and root 2 not the root. And then we'll tack on units, which is in feet. I think like if you see this in the book, they'll put parentheses around it. So that would be our perimeter. And if you wanted to know what that answer actually was, you could type it in your calculator to get decimal approximation. So on the back, what we're going to see is adding things that do not have right radicals. What we can do with those. Okay, so on the back we see simplified. And if you were to look at it right off the bat, you'd think, oh, not possible. They don't match. Those are just the different numbers. Okay, but before you say not possible, you do need to simplify all of the radicals first. Then add or subtract. So we're going to use, these are all square roots, right? We're going to use our perfect squares list to break square roots down into its simplest form. So 50. What would I break 50 into? Good. Square root of 25, square root of 2. Okay, there is an outside number of 3, so you want to bring that down. Plus 3. And then what am I going to break 32 into? Summer? Good. 16 and 2. You don't want to choose 8 and 4. You could, but you have to then break it down again. Break 8 down into 4 and 2. And then our last part, bring down your minus 5. And we'll break the 18 into 9 and 2. Now we'll go ahead and take our square roots, what we know. So the square root of 25 is 5. The square root of 16 is 4. And the square root of 9 is 3. So I'm left with 5 square roots of 2. Plus, now be careful, you may want to add this to your notes. You are multiplying the 3 and the 4 together. Okay, because it was 3 times the square root of 16. So that's 3 times 4, which is 12 square root of 16. The same thing with the next two numbers. I have 5 and 3, which I'm going to multiply to get minus 15 square root. So now I have like radicals all the way through the problem. So just add and subtract from left to right. 5 and 12 gets me 17 square root of 2 minus 15 square root of 2. Final answer, 2 square root. And there's not really a way to check your answer on these. You could type this whole thing in your calculator, get a decimal number, and type this whole number in your calculator and get another decimal function to make sure they match. But that's still not going to ensure that you simplify completely necessarily. But it could check to make sure you didn't change the answer. Okay, the next one we're going to do the same thing. We're going to break up our square roots if possible. So 20 will go into 4 and 5. What would 45 go into? 9 and 5. Don't forget about the outside numbers that were there, the plus 4. Now 80, what would I break that into? Friend? Perfect. If you do 4 and 20, you would then have to break 20 down into 4 and 5. So your best bet is that largest perfect square. So again, take your perfect squares and multiply any outside numbers along with the new outside numbers. We should get 6 square root of 5 minus 3 square root of 5 plus, multiplying those together, 16 square root of 5. Add or subtract from left to right, so 6 minus 3 is 3 square root of 5, and adding 16, we should get 19 square root. The rest of the problems are going to involve multiplying and dividing. So stuff that we've looked at, but without a binomial. So today we're going to see two things being added or subtracted that are radicals. What do you think my first step for number 11 would be? Let's say to multiply using FOIL. So you guys see a quantity squared. Evan? Good. Expand this. If there was not a minus right here, then you could just square the 2, square the 3, and square the square root of 2. But since this is having a binomial, we do need to expand it. So square root of 2 minus square root of 3 times the quantity square root of 2 minus 3. And then you just go to town and FOIL. Be careful. The square root of 2 times the square root of 2 is the square root of 4. Minus the square root of 6. Minus the square root of 6. And then the last terms we have two negatives make a positive. This should be a square root of 9. We did this in chapter 6 a lot, but we have like x's involved. X minuses. Okay, take your square roots. So this is 2. This is 3. And these are like radicals, so you can combine them. So I have 2 plus 3, which is 5. I have negative 1 square root of 6 minus 1 square root of 6, which would be minus 2 square roots of 6. Typically, the number comes first, and then the irrational number comes second. This is how we used to see complex numbers. Okay, the next one has inside and outside numbers, so just be careful. We'll FOIL. 2 times 1 is 2. Now, when you multiply 2 times negative 5 square root of 3, you're only multiplying the 2 and the 5 together. So this will get me a minus 10 square root of 3. It does not become square root of 6. And then plus 4 square root of 3. And positive 4 times negative 5 is negative 20. Square root of 3 times the square root of 3 is the square root of 9. 9, 9, 9. So you don't have to read them. Okay, now we can take the square root of 9, which is 3. And we can also combine our like radicals. So we'll have 2, negative 2 plus 4 is a negative 6 square root of 3. Don't forget that you are multiplying those numbers together. So negative 20 times 3 is a negative 60. Then we'll combine 2 and negative 60, which should get me a negative 58 minus 6 square root. Okay, we are going to skip number 14, but I do want to take a look at 13. Do you see how these binomials are almost the same, but one's positive and one's negative? Does anyone remember what those are called from chapter 6? Starts with a C. C-O. Conjugate. Okay, so these are called conjugates. Okay, conjugates are used a lot to help you get rid of square roots. Okay, conjugates are in the form a plus the square root of b and a minus the square root of b. We did this in chapter 6. If this was a root, then this had to be a root also because of our irrational root theorem. All right, but in this case, we're not solving for them. We're just FOILing them. So watch what happens. We'll get 3 times 2 is 9. 3 times negative square root of 7 is minus 3 square root of 7. Plus 3 square root of 7. And we'll get a negative square root of 49. So you can see negative 3 plus 3, that goes to 0. So those are going to cancel each other. The square root of 49 is just 7. So I'm left with just 9 minus 7, which is 2. Oh, it's a lot better than what we started out with, right? Okay, so we're going to use this conjugate idea to help us rationalize the denominator. Okay. We're going to skip over 14 because it's kind of the same thing. We do want to get to 15. Plenty of time. All right, so number 15 and 16 ask us to rationalize the denominator. Notice that the denominator is a binomial. So if the denominator is a binomial, meaning something is being added or subtracted, two things, you cannot just multiply by what's in the denominator. If you do, you multiply by 4 plus the square root of 3, you're not going to get rid of the square root, which is the whole goal. If you have two positives or two negatives, you're going to end up getting a something square root of something in your answer. So when we rationalize the denominator, if it is a binomial, we are going to multiply the numerator and denominator by the conjugate of the denominator. That will allow us to eliminate square roots in the denominator. Also, since we have binomials, you may want to put parentheses around them to remind yourself for FOIL. Okay. So I need to find the conjugate of the denominator. Four plus the square root of 3, the conjugate would be 4 minus the square root of 3. Whatever you do to the denominator, you must do to the numerator. Then we have to FOIL both the numerator and denominator. So lots of FOILing. So we'll get 2 times 4, which is 8, minus 2 square root of 3, minus 4 square root of 3. And our two negatives will make a positive square root of 9, 3 times 3. In the denominator, if we've done our job correctly, we should get rid of our square roots. So we'll get 4 times 4 is 16, minus 4 square root of 3, plus 4 square root of 3, minus the square root of 9. And we FOIL that denominator. So let's check it out. Yes, a negative and a positive go to 0. And I still have the square root of 9, but I know what that is. That's just 3. Then the denominator, I'm going to get 16 minus 3, which is going to be just a number of 13. Now in the numerator, I do have to do a little bit of work as well. The square root of 9 up here is 3, but we're adding 8 plus 3 is 11. And then we have combining like radicals, negative 2 minus 4 would be minus 6 square root of 3. So my final answer should be 11 minus 6 square root of 3 all over 3. Okay, the next one will be the same process. Again, we want to put parentheses around this. We're going to rationalize the denominator by multiplying by the conjugate of the denominator, which should be 4 plus the square root of 15. I want you guys to see if you can FOIL, distribute, and simplify. And we'll come back to share our answer. what do we got as our final answer? After we simplified. Emily? 39 plus 10 squared to 15, technically all over 1. Anything over 1 is a default, so we can leave that off, or if you leave it, that's also fine. Okay, the homework then is posted on my website, 7.3 assignment. The answers are also provided inside that same document, so you just have to scroll down. I did put up the review guide. It's not a study guide, it's just your chapter review from the textbook. But that's what I'm going to be assigning on Friday to help you study for the test Monday. So if anyone wants to get a head start on it, it is posted. And we still have 2 more sections to learn, 7.4, day 1 and 2, which will be tomorrow and Thursday.